All right, so we move into chapter entitled Internal Flow. What was the previous chapter's title? External flow. Internal, you're within a pipe, you're within a duct. So we're going to go back and review fluid mechanics, hydrodynamic considerations before we add in thermal considerations. Energy balance, then you can get results for laminar flow as well as turbulent flow. All right. Let's jump into it. Again, this is beginning with a lot of review. So we have a wall, a pipe. You have to get into the pipe. So somehow you have fluid that's going to come into the pipe from a large tank. And when it first comes in, it's like flow over a flat plate. You have the development of a boundary layer which goes further and further out from the wall until basically it's fully developed, where the presence of the wall of the pipe is felt throughout the throughout the pipe. So the fluid flow, if you looked at a profile here, it would be pretty flat velocity profile. And then down here, the velocity profile, if it's laminar flow, would look very quadratic. If it's turbulent flow, it'd have a little different shape to it. And so once the velocity profile is fully developed, does the velocity profile change as it goes down the tube? How would it change, the velocity profile change? I mean, it's not going to speed up or slow down anymore. We're going to do constant density. Density is equal to a constant, so it's not like it's expanding, hence speeding up as it's going down the pipe. It's fully developed. Incompressible. The velocity profile quits changing. But before it becomes fully developed, you have a flat spot and then more of a change in the velocity profile until it becomes fully developed. So this region in here is what we call the entrance region, and this region over there is the fully developed. What is it? What is being developed? The boundary layer, the velocity profile. It becomes hydrodynamically fully developed. Well, we have a Reynolds number for flow inside of a pipe. We use the characteristic diameter D for the inside diameters, our length in the Reynolds number. So we'd have rho, some velocity, some average velocity, some mean velocity for the fluid in the pipe, D over mu. So U sub M is mean. Not mean like nasty, but mean like average. Average velocity. So if it's have a parabolic profile like this, it's not the center line. This would be the center line, right? In a pipe. That CL center line symbol. It's not the center line velocity, but it's the average velocity over that cross-sectional area. We'd like the mean velocity to be very useful, and so if I said calculate the mass flow rate down the pipe, you'd say, oh, well, that's the density times that appropriate mean velocity times the cross-sectional area. True? So we can replace U sub M as the mass flow rate divided by rho, and then the cross-sectional area is pi diameter squared over 4. So now I could take that result for the mean velocity, replace it in the Reynolds number, m dot 4 divided by rho pi d squared mu d. All right, let's cancel some terms. The rho's go, one of the d's go. And so what are you left with? That the Reynolds number, you can also write it as 4 m dot over pi d mu. That would be the Reynolds number for flow in a pipe. A lot of times we add a subscript d on that Reynolds number so that we know what is the characteristic length. All right, let's do a clicker question, huh? So here's our clicker question. For pipe flow, the critical Reynolds number is either 2,300 or 500,000. So what do you mean by critical Reynolds number? Well, If you have a flow above that, it's turbulent. If it's below that, it's laminar flow in the pipe. All right, we'll go ahead and stop. And there's two critical Reynolds numbers that we have to remember for this class. I mean, there's other ones, but just two. And there's flow over knife edge plate. That critical Reynolds number is 500,000. It's measured from the leading edge. X increases as it goes down. Here, it's not X in the Reynolds number for internal flow in a pipe. It's the diameter. So the Reynolds number doesn't continue to increase as you go further down the pipe, does it? No. But it tells us, is that flow going to be turbulent or is that flow going to be laminar? And some books will have 2100, some books will have 2000, most books will have around 2300 for that critical Reynolds number. So there you go. This was, B was the correct answer for flow over a flat plate. How far does one have to go to become fully developed hydrodynamically? How far into the pipe before it becomes fully developed? Well, if the Reynolds number is less than 2300, it's going to be Reynolds laminar flow. If it's laminar, it's 1/20th the diameter times the Reynolds number. What happens if the Reynolds number is greater than 2300? I anticipate turbulent flow. Then it actually develops quite quickly. It's controlled by the growth of the boundary layer. Remember, flow over a flat plate, when it turned turbulent, that the extent of the boundary layer jumped. And so the distance that you have to go down from the inlet of the pipe to become fully developed hydrodynamically is only 10 diameters. Well, let's check on this. Let's say that somebody says the Reynolds number is 200. How far do I have to go to become fully developed hydrodynamically? Well, I'm going to say, I'm going to use the first equation. I'll put Reynolds of 200. It'll give me 10 diameters, won't it? All right, somebody says put in 2,000. If I said the Reynolds number is 2,000, they say, well, it's probably going to be right at that cusp, but let me say it's still laminar. I'll say it's just going to not, if I increase the flow a little bit more, it's not going to be laminar, it's going to be turbulent. This will be the upper extent to being laminar flow. All right, so we put in Reynolds number of 2,000, and it's 100 diameters. That's a big change, isn't it? From 10 to 100 diameters. Let's say the person says, no, now it's 20,000. That's the Reynolds number. What do? We say, well, don't use the first equation, use the second equation. You're back down to 10 diameters. So entrance lengths, you can have more of a discussion on it, but for a laminar flow, it's anywhere from about 10, I know this is rough, about 10 diameters up to about 60 diameters. It's pretty hard to really get it to go to 100 diameters, even though the calculation just showed 100 diameters. But that would be fully developed hydrodynamically. And then for the turbulent flow, well, 10 diameters. A lot of cases we have turbulent flow. Let's talk about the mean velocity. So we talk a pipe, and you have the center line of the pipe. It will turn it and look at it, a projection looking down the pipe, and there's that center line. And we'll talk about two coordinates to help describe things. We'll talk about the R and the X. X is down the length of the pipe in the direction of flow. R is a radius. Goes from, what does R go from? 0 to cap R, the radius, internal radius of the pipe. And we're interested, we know that we're going to eventually be able to solve for U as a function of R. So we'll have that velocity profile. But we just want to know what is the equation for the mean velocity use of M. That's the mean velocity. Well, the way to get the equation for the mean velocity is think about the mass flow rate over a cross section So the mass flow rate over a cross section, how do I calculate that? Thinking about over different areas, the velocity is faster when r is small at 0, and then as r goes out to cap r, the velocity goes down and down. Well, you do an integration, don't you? So think about going out to a location r. R plus dr gives you a little, what do you call that? Constant velocity element. And so what is this area of this little element that I'm going to now integrate over? Is it 2 pi r dr from calculus? 2 pi r dr? So what we have is, if you're going to do the sum of the flows over different rings, that's going to be the integral of rho u as a function of r dA. And we want a very simple equation for the mass flow rate. We want it to be u mean times the cross-sectional area. This gives us the equation for the mean velocity. Cancel the rows. We're not getting really sophisticated where we have to account for density difference in that cross-section. All right. And so the mean velocity is 1 over the cross-sectional area, the integral of u dA. If you wanted to try and do that integration, I'd put 1 over pi cap r squared integral u times 2 pi r dr. But this is the more generic equation, isn't it? Okay. That's how you would calculate the mean velocity. Well, what about laminar flow fully developed velocity profile? Can we get that velocity profile? Can we get u as a function of r when we have laminar flow down the pipe and it's fully developed? Well, yes, and the way we do that is we consider the x momentum equation, and I'm not going to start with the most generic in the cylindrical coordinates, but just write it with all the zero terms removed from the x momentum equation, and you get a differential equation that reads the viscosity divided by r, the rate of change with respect to r, of r du dr. That's equal to dp dx. Pressure as you go down the pipe typically goes down because it's being pushed to overcome the effects of viscosity. All right. You also have boundary condition number 1, and you would get that at r equal to 0. What is the boundary condition at r equal to 0? du dr at 0 is equal to 0. How do you describe that mathematically in words? It's mathematically written, but what is it in words? This first boundary condition. It's symmetrical. It's symmetrical, right? All right. How about another boundary condition, number 2? U at cap r is equal to 0. Describe that in words. No slip at the wall. No slip at the wall. Okay. Now we have a well-posed mathematical problem. How do we want to solve that? Separate, integrate. True? So when you separate, I can leave the mu over here, and what we'll do is we'll put the dp dx, we'll put that r dr over there, and then we left with derivative of r du dr. That's my separate. Then we integrate. The mu is constant, dp dx is constant, and you come in with mu r du dr is equal to dp dx. I like to put parentheses around this dp dx, be treating it as a quantity. It's the pressure gradient down the length of the pipe. Okay, what do we pick up here? 1/2 r squared plus the first constant of integration. What do? We apply the first boundary condition. Can't spell apply. Boundary condition number 1, what does it give us? C10. Let's continue. So now we're going to separate again. So you'll get mu du is equal to dp dx 1/2 r squared, but we bring over dr over r, so it cancels one of those. What's the next step? Integrate. And so you'll have mu u is equal to dp dx 1/4 r squared plus a second constant of integration. So when we apply the second boundary condition, what do we pick up? We pick up that C1 is equal to r squared over 4 minus dp dx. I grouped that negative sign with the dp dx. All right. So you can rewrite then u as a function of r, or just say u is equal to the r squared over 4 minus dp dx times 1 minus r over cap r squared. And that's our quadratic. That's our parabolic. That's our velocity profile. Where is the maximum? U max is when u at r is equal to 0. And what does that come in at? It comes in at r squared divided by 4 minus dp dx. So that's our maximum velocity. So you could write u is equal to u max times 1 minus r over cap r squared. Make your professor happy here. Look very familiar? All heads nod up and down yes in the affirmative. Absolutely. You're almost putting me to sleep. Professor, this is old school. Just straight out of fluids. True? All right. So now I want to calculate that mean velocity for the fully developed laminar flow. Well, what was our equation for the mean velocity? U sub m was 1 over the cross-sectional area, the integral of u dA, which, hey, we said that we're going to integrate pi r squared. And now we finally have u. What is it? It's u max times 1 minus lowercase r over cap r squared. Isn't that what u is? Times 2 pi r dr, integrate from 0 to cap r. That's um. Thumbs up if you agree. Now the clicker question. I think you could do the math, but from your fluid mechanics background, the mean velocity, what we're doing right here is we're solving for an analytic expression for the mean velocity, u sub m, for fully developed laminar flow in a pipe is blank the max velocity. What was the max velocity? That. Is it twice the max velocity, half, 1/3, 1/4, or 1/5? Your recall. What do you say? Everybody in? Here goes the stop. Boom. Professor, it'd been a lot easier if you'd have just finished that integral. Right? Isn't that the point of this integral? But what's your memory say? It's 1/2. 1/2 the max. The center line, the average or the mean velocity fully developed laminar flow of the pipe is 1/2 of the center line or the maximum velocity. Well, let's flush it out in detail now. So let me get rid of this. And so what we're going to do is we're going to say u mean is equal to u max times a whole bunch. But let's cancel the pi. And we'll have a 2 integral from 0 to 1. What I'm going to do is I'm going to bring in, I brought this 2 outside, true, as well as that u max outside. This r squared, we're going to come inside and distribute it over here. And so I'm going to introduce a variable, let's call it tau, which is lowercase r over cap r. And so we're going to integrate 1 minus tau squared, tau d tau from tau 0 to tau 1. Did I lose anybody? Does that look okay? Yes.
At the front, isn't it r
Yeah, this is r squared. And so we bring that inside, and we have then an r there and an r there. So that gives us the tau d tau. And this is already tau right there. And so what we're going to pick up u max times 2, the integral. Now, I might as well just make it easy on myself. I'll say it's a tau minus tau cubed d tau, right? Did I do that correctly? I need to get rid of this box, I think. Get it out of the way. Okay, so it's equal to 2, well, just leave u max here. U max times 2 times, now, integral tau d tau, 1/2 tau squared, minus the integral tau cubed, evaluated tau goes from 0 to 1, and what are you left with from all of this? 1/2 minus 1/4, which is a positive 1/4. And so 1/4 times 2 times u max. So u mean is equal to 1/2 u max. Did I mention that this is one of my sayings I say every class? I've said it probably 10, 20 years, whatever, how long I've been teaching, is that if it's important, you probably see it in at least 2 classes. And if it's really, really important, you'll see it in 3 classes. So, you know, something about integration, you see it in the calculus, see it in the physics, see it in another class, something about centroids, center of mass, center of gravity, moments of inertia. And here it is for velocity. You probably saw it in fluids. You probably saw it in physics. You saw it in another class, this class. So it's really important. So now let's take a look at constructing either, you could think about it as a control volume and do a linear momentum analysis of that control volume, or a free body diagram and do a force balance on it. Of what? Of the fluid that's in a section of the pipe. So this is only the fluid. It's in a section of pipe. The section is of length delta x. What are the boundary forces acting on it? Well, we have acting over this whole front face, the pressure at location x. How about on the back face? The pressure at location x plus delta x. And then everywhere around that surface area is surface shear stress. You can go back and do a linear momentum. You have mass flow coming in and out of that control volume, but it's fully developed, hence the linear momentum flow rate's not changing. It really just boils down to a free body diagram and a force balance. What does that force balance give us? Well, it says that what's pushing it in the positive x direction, I should have put that down there like that, minus pushing back times the cross-sectional area is equal to the wall shear stress times how much wall area there is. Wouldn't that be pi d times delta x? I pause and I look at that. Is that good? What do you think we do with that delta x? Bring that delta x to this side. What does it do to this ratio? As the limit as delta x becomes smaller, it becomes the derivative. And it becomes negative dp dx. And then we have the cross-sectional area. What's the cross-sectional area? Pi d squared over 4 times the wall shear stress shear stress at the wall times pi d. Can we cancel the pi's? Can we cancel one of the d's? And we're left with this very interesting result. And when we talked about flow over a flat plate, we normalized that shear stress at the wall, didn't we? Or the shear stress at the surface. What did we normalize it by? And we introduced C sub f, didn't we? Well, we're going to do the same thing here. So we'll introduce a friction coefficient or friction factor, C sub f. Remember, it was tau for a flat plate, flow over a flat plate at the surface divided by 1/2 rho u infinity squared. But now we're going to think about it. I know where I evaluate that tau at the surface. That's my pipe wall. But I should use not u infinity. I use u mean, the mean velocity squared. That's appropriate friction coefficient for pipe flow. Well, I can now replace what I had for the shear stress at the wall. Wasn't that d divided by 4 minus dp dx? Sure. And then the rest of the equation, 1/2 rho u mean squared. And so this is our equation for C sub f. Sometimes it's also called a friction factor, but a fanning friction factor after somebody who did a lot of work in fluid mechanics. So fanning friction factor for pipe flow. So it's dp dx with a minus sign because it's decreasing pressure as you go down the length of the pipe. Diameter over 4, etc. Well, we're going to show the Moody diagram on the next slide. And the Moody diagram has the Darcy-Weisbach friction factor. A lot of times there's no subscript on it, but when there's a potential confusion, I add subscripts. And so the Moody diagram friction factor is defined as minus dp dx, this is straight out of the fluids, times the diameter d divided by 1/2 rho u mean squared. I take a look. Oh, I got the dp dx right there. I've got the d, and I've got 1/2 rho. So the relationship between the fanning friction factor, based on a skin friction coefficient, and the Moody diagram friction factor is F over 4. So it's a little possibly confusing. Why do I like to, and why do a lot of people still like this fanning friction factor? Well, you take the fanning friction factor, C sub F, you divide it by 2, F fanning divided by 2, and that's equal to the Moody diagram or Darcy-Weisbach friction factor divided by 8. Not doing much, but this should jog our memory. C sub F over 2, C sub F over 2. Chapter 6, the very end of chapter 6, the introduction to convection. There was an analogy. It was the modified Reynolds analogy. What was on the left side of the equation side in the modified Reynolds analogy? C sub F over 2. And so in the modified Reynolds analogy, C sub F over 2 is equal to the Stanton times the Prandtl to the 2/3, or you could just put the Nusselt divided by Reynolds, Prandtl to the 1/3. So in the hunt, the challenge to find a Nusselt correlation for a lot of problems in internal flow is just take C sub F over 2 multiplied by a Reynolds number times a Prandtl to the 1/3. I'm going to build on that in the next slide or two. So that's why we just don't throw out the fanning friction factor completely. So this is our Moody diagram. Maybe if you took me for fluids, maybe I asked this question. I would sometimes do it. Here's a blank sheet of paper for 25% of the exam. From memory, sketch the Moody diagram with as much detail and as accurately as you can. Did I do that with you? Were you in? No? No? It's a good question. I like to do that because sometimes we look at these and, I got it. But let's take a look. What's on the x-axis? Reynolds number. What scale is it? Linear or log? Log. Does it cover a large territory, a large range? It's a tremendous range. So it goes from, let's say, 1,000, 10,000, 100,000, million, 10 million, 100 million. That's a large range of values. And now we remember when it's below around 2,000 or 2,300, what do we know about the flow? So most of the Moody diagram is not describing laminar flow, it's describing turbulent flow in a pipe, isn't it? But there is the laminar flow correlation. We haven't derived it, but the friction factor is equal to 64 over Reynolds number. It's plotted there as a straight line. Well, what's on the y-axis? The friction factor. It's the Darcy-Weisbach friction factor. Okay. Is it log scale or linear scale? It's logarithmic scale. Does it have as huge of a variation as the Reynolds did? No. It really only goes from 0.01 to 0.1. Why do they put that on a log scale? Well, it spreads it out, even though it's only a factor of 10. Where here it was a factor 10, 100, 1,000, 10,000, 100,000 factor, right? Okay. So now that we have the range here, a lot of times somebody says, oh, I don't know what the friction factor should be close to. Well, if somebody gave you a friction factor, said it was 0.001, what do you think? Look for your error. It's not on the diagram. It's not in the range of conditions that we would experience. How about somebody says the friction factor is 0.38? What do you think? That's why knowing this range is good, so it helps you what's reasonable. In the grand scheme of things, there's a whole lot of action in this range of friction factor. Just a lot of action. Okay. Now let's take a look. What happens when you're done with the laminar flow? You have to somehow transition to turbulent flow. Do these lines nicely connect? No. They leave it to your imagination. Will they actually be connected? Yeah, they will, but it's hard to say with experimental clarity that that's how the curve transitions, because what do we have for all these red curves? What are they changing? The relative roughness. Relative roughness varies and goes up. Isn't this for a rougher pipe? Isn't it? Where's the smoothest of the smooth pipe? The lowest curve on this Moody diagram. So somehow you're transitioning, and probably for a rougher pipe, it's going to stop being laminar before 2300 and start that transition, because those bumps on the sidewall will trip it to be turbulent. So you have this region out here. It has a funny name, one of the funniest names. What is that zone called? Fully rough. You pull out a different fluids book, they'll say fully turbulent. Pull out a different complete turbulence. It'll be different names and different texts. Yeah.
Why would someone use a really, really rough pipe?
Pardon?
Why would someone use a really
well, you may have it because it's an old pipe that's been in service for a while, and there's some debris or stuff that ends up on the sidewalls that blocks the flow passage and gives it that roughness. But down here they'd say if you have drawn tubing, the roughness of the drawn tubing is very low. Do we ever have engineering applications with drawn tubing? Yeah, copper, drawn tubing. A lot of copper tubes and fluids flowing through them. And then you have commercial steel. Yeah, that's a little rougher. We have a lot of flow in commercial steel. Cast iron, a little rougher. And then the very rough would be, you do have some flow in concrete, but that's more of a civil engineering application, isn't it? But yes, so that you can get the rougher pipe, and you have that fully rough zone or fully turbulent or complete turbulence region. What is this line here doing? This is where a lot of students will mess up. They don't understand. What is that line? It separates a region in the Moody diagram that's turbulent on this side and turbulent on that side, but there's a different characteristic between the two. To the right of that dashed line, There's a particular characteristic in that turbulent region, and to the left, there's a particular characteristic. Ready for a clicker question? So, in the fully rough zone, professor, remind me, where's that fully rough zone? Well, here's the name of it. The friction factor is a function of the relative roughness and Reynolds number, A, or Reynolds number only, or relative roughness only. Aren't I looking typically for a friction factor? Is the friction factor in the fully rough zone a function of the relative roughness and the Reynolds number, or is the friction factor a function of the Reynolds number only, or the friction factor a function of the relative roughness only? Everybody in? Well, let's answer this question. Somebody says, how do you use the Moody diagram? The way we've outlined it, you're trying to get this output from some inputs. So do this if I said it was 10 to the, let's just pick an easy one, 10 to the 7. That's the Reynolds number. And I came up and I said, okay, the friction factor is whatever this number is, 0.0002. Right here is the intersection of that relative roughness line with that Reynolds number line. Hence, to read off the friction factor, F, I come over and I read it. True? So at that point, am I in the fully rough zone? Yeah, we're in the fully rough zone. Play the mind game. Let's change the Reynolds number. Let's boost it up by a factor of 2. Isn't that increase the Reynolds number? So I'm going to change the Reynolds number but not change the relative roughness. Did the friction factor change? No. Cut the Reynolds number without changing the relative roughness. Did it change the friction factor? No. Then play the other game. Don't change the Reynolds number. Leave the Reynolds number at 10 to the 7 and change the relative roughness. So somehow you have a rougher pipe. Did the friction factor change? Did the friction? Yes, it did. So did it help you figure out which is the best answer? So which is it? In that complete turbulence, in that fully rough zone, the friction factor no longer is a function of the Reynolds number. It is not a function of the Reynolds number anymore. It's a function only of the relative roughness. Let's talk a little bit about this zone right in here. That zone, it's turbulent. The friction factor is a function of both of them. Both of them. How about for the smooth? Well, first of all, if it's smooth, what's the relative roughness? 0. That's right. So it's only a function of Reynolds number. For smooth, it's a function of the Reynolds number only. In this region, it's a function of the Reynolds number and relative roughness. In the complete or fully turbulent or fully rough region, it's a function only of relative roughness. How about the laminar? I looked a lot of books, and do they have laminar flow as a function of Reynolds number and relative roughness anywhere? Nope, it's always a smooth tube. 64 of a Reynolds number is only for a smooth tube in the laminar region. All right. Now, one thing is they will fit a lot of curves to smooth tube data. One of them, old one, the Blasius correlation. What's it look like? It looks like a constant times Reynolds to a power 0.25. This was F, true? What was C sub F over 2 equal to? Friction factor over 8. Guess what? We just have an expression for the friction factor from the Moody diagram. You can substitute it into that. True? So if you want to, you can get a Nusselt correlation for smooth tube turbulent flow just using that information right there. What was our modified Reynolds analogy? C sub F divided by 2 is a Newton. I mean, not Newton. Nusselt divided by Reynolds Prandtl to the 1/3. So the Nusselt is equal to C sub F over 2, Reynolds Prandtl to the 1/3. I can get my first convective correlation, that easy. And so this number is friction factor over 8. If I use the Blasius correlation, what I pick up is that the Nusselt number is equal to 0.04. I know there's some other digits on there. Reynolds to the 0.75, Prandtl to the 1/3. Somebody goes back to the Moody diagram and they want to curve fit a different way, and they get that the friction factor is not quite that one, but it's 0.192 divided by the Reynolds to the 0.2. And that's easily done, and when I teach a graduate class, I usually make them do that. Just go back and curve fit a couple points for the smooth tube, and you'll get often an easy expression like this. Then you put that into the modified Reynolds analogy, and you'll get another Nusselt number is equal to 0.0245 Reynolds to the 0.8, Prandtl to the 1/3. And the form of the equation starts to appear. Oh, the Nusselt is a constant. Reynolds to a power, about 0.8. Prandtl to a 1/3. And that's very common in forced convection. Smooth tube, fully developed turbulent flow. Well, let's finish with this slide. So we're interested in calculating the pressure loss. The pressure loss unraveling the friction factor would be F, the friction factor, times the length over diameter. If I have a longer pipe and it's scaled by the diameter, then I have more pressure drop, times the 1/2 rho, the mean velocity squared, the velocity pressure. Then the fluid pumping power required to overcome the pressure drop. So think about, I have a pump, and the pump ingests some fluid. I'm going to try and draw it like this, and throws that fluid out. And so I have state 1 on the inlet to the pump and state 2 on the exit to the pump. Is there a pressure gain across the pump? That's the purpose of the pump, isn't it? The pressure gain. But then the pipe goes out to a system and goes around. So we have the pressure gain by the pump, but the pressure gain by the pump is equal to the pressure loss by the system, pushing it through the pipes. And a simple equation for that, if it's just a bunch of straight pipes, F L over D 1/2 rho U M squared. All right. How do I make the pump run? I have a shaft coming to the pump. What drives it? Electric motor. Electric motor. Okay. What drives the electric motor? Current, alternating current, power, electric power. So we have 3 concepts of power. W dot electric. So many horsepower or kilowatts coming in electric power to the motor. Some of it's converted into shaft power, a percent. The efficiency of the motor is that fraction that's converted electric power into shaft power. Then from the shaft in the pump, we have the efficiency of the pump. Some of it gets into the fluid power. That fluid power, then as the flow goes around the loop, is dissipated, and it has to get back to the pump to get that power put back into it, or the energy per unit mass put back into it. So we suspect that that fluid power is equal to the pressure gain, which is the pressure loss, times something. And underneath this box for the last clicker question of the day, what is it times? What's this fluid power? This fluid power is the pressure loss times something. Is it m dot? Is it rho m dot? M dot over rho, M dot over G, or M dot over rho G? Is everybody in? All right, let's just shut it down. So let me do this. In the SI units, what are the units on the fluid power? W dot fluid. Watts. Would that watt be a joule per second? A joule per second. Help me with P sub L, pressure loss. Units, SI. Pascal, newtons per meter squared. So just from the units, what I need is I need to multiply by something here, right? I think what I'm going to need is I'm going to have something that's per unit second. Okay, that's good. And if I have a meter here, a newton times a meter is a joule, wouldn't it be? But I have that pesky meter squared there, so I'll put a meter squared there. Will that work? Will then the meter squared go, and then, so what I'm looking for has to have units. I can just tell from the units. Meters cubed per second. What are the units of M dot? Kilogram per second. What are the units of rho? Well, that'd be kilogram squared per second. What about M dot divided by rho? Meter cubed per second. M dot divided by G. Well, all right, we got to figure that out. Kilogram per second, and then we have meter per second squared. So kilogram second per meter. No, that's not going to work. We already have what's going to work, right? What's going to work? Thank you for your attention. Please read this chapter. It's a very important chapter. Please master it.